What started as a curiosity about Microsoft disk operating systems, viruses in the early 90s, turned into a career that has redefined how we understand software. Our first speaker is the Vice President of Software Assurance at Oracle and an adjunct professor at the University of Queensland. Throughout her career, from founding Oracle Labs Australia to releasing tools used by thousands of developers daily, she has remained at the absolute forefront of program analysis. She is a mentor, a scholar, and a visionary who has shaped the intersection of security and machine learning. To share her incredible retrospective on the evolution of the compilation, please join me in welcoming the Lifetime Achievement Awarded Mother of the Compilation, Dr. Cristina Cifuentes.
Thank you, Guilherme, and boa tarde. I'm really happy to be here in Lisboa today to be able to talk to you about this work that started 32 years ago when I submitted my PhD thesis on decompilation techniques. I'm Cristina Cifuentes, and today we're going to start through the memory lane, thinking back about how the world has changed. So back in 1994, I submitted my PhD thesis on decompilation techniques. And 2 years ago, I posted on LinkedIn this message because it was just amazing to think back 30 years later. Techniques that people didn't really know and understand about are now being widely used by the computer security community in the form of decompilers. So how many of you use decompilation or decompilers? Okay, yes, some of you. So for those of you that are not fully familiar with decompilers, here's the super quick summary about decompilation. You normally take a source level program written in whichever language. I happen to have done most of my work with the C language, but of course you can have other languages like Java and so on. So you take that code and the compiler is going to convert it into machine code. And so here's the binary hexadecimal representation of that particular function that I had shown you, a Fibonacci function. Now, when you start doing decompilation, what you're going to do is the inverse of the compilation process. So by doing it inverse, what you want to do is take this representation and convert it back into the assembly code for it. You can clearly see here that you have multiple different calls. It's all x86 code. And then the next step is to be able to lift that level of representation further up to the high-level programming language. So this is C code. It resembles the original language code that we had, but as you can see, there are no variable names per se that match the original code because the binaries were stripped. They didn't have that information. So the decompiler will create whichever names it feels like it, and normally it interacts with users. So in essence, a decompiler is a tool that is going to take as input a machine code program, a binary program, and it's going to convert it into another program that has a high-level representation. That high-level representation may be in another common language like C or Java or so on, or it could be an intermediate representation as well. Now, this talk is dedicated to my dad. Today, 4 years ago, my dad passed away. And it was thanks to him that I started to study computer science. If you can imagine, 17-year-old girl living in Colombia, in Bogota, Colombia. No one had PCs at their homes back then. That tells you my age. And my dad says, there's a future in computing. And that's how I ended up studying computer science, just purely based on that vision. So thanks to my dad, I did computer science. And not only that, how did I end up doing a PhD back in 1991? Because at the time, I was studying at the Queensland University of Technology in Australia, and I had really enjoyed the compiler subject. So I ended up doing a compilers project for like 6 months, and then I ended up doing a summer internship with Professor John Gove, who ended up being my PhD advisor. Now, at the time, here was the interesting thing. Students used to work on the Modula 2 compiler. Like all of the assignments were Modula 2 at the Queensland University of Technology, QUT. And at the time, now PCs were common. Everyone had PCs at home. Most students had PCs at home, but the compiler only used to work on Unix machines. So Unix machines were 32 bits, PCs were 16 bits. The amount of memory was clearly different. You only had 640 kilobytes of memory in your PCs back then. And so the idea was, how do we enable students to be able to run their assignments and do their assignments at home? And so the representation for the Modula 2 compiler already had like 2 different translators. So the idea from John was to be able to add a 3rd translator. And with that 3rd translator, that 3rd translator, the idea was really just to have an intermediate representation that was called decode to be able to generate an interpreter for x86, because amount of memory was an issue, right? And you only had like 2 floppy disks that you could use in order to be able to run these programs as well. In order to do like all of the initialization that the compiler needs, that was already 400 kilobytes. And remember, memory was 640 kilobytes at the time. So very time constrained, memory constrained. And so my role was to be able to work on the decode interpreter. And I was generating a lot of assembly code. I became very fluent on assembly code. And by the end of the summer internship, we had like a fully working implementation. Students were able to use it like the next year at home. And they had to use 2 floppy drives, 5.25 inch floppy drives to be able to run their assignments. It was a success with the students. It enabled them to do what they needed to do. And one thing that I learned is that professors tend to publish some of their new novel work. And so in 1992, a paper was published on this work at the Australian Computer Science Conference. So with that background of the end of my undergraduate degree, that's what really led to me doing a PhD in this area of decompilation. I was fluent on reading binaries, reading assembly code from those binaries. And just to give you a little bit of an idea as to how the world was back in 1991 when I started my PhD thesis, at the time, websites were not popular. It was actually in August 1991 that the first CERN website became available. Okay? There were various different types of processors, like 386 and Intel, like the low-cost i486SX. And Apple had a PowerBook laptop. It was, pretty large, but it was using Motorola chips back then, right? And the operating system that was most common was the Microsoft Disk operating system, also known as the DOS operating system. All of us used to use that back then. Also, more importantly, the Linux kernel by Linus Torvalds only became available in August of that year. So that gives you a little bit of an idea as to what the world looked like. Now, further to that, what was happening now that PCs were common at home? Viruses started becoming common. And in 1991, there were lots of different viruses that started to really affect PCs, not only like because the virus was available, but also because virus construction sets became available. And so more people started like learning how to write viruses because they thought it was fun, right? But clearly from a computer security point of view, this is an issue, right? And so professors, in the Information Security Center at QUT, and also my compilers professor, they started discussing about this. Well, what are we going to do about viruses? There was a company that was, the company Symantec, that actually released the Norton antiviruses software back in that year. And that was doing pattern matching initially, right? And so we were interested in looking into, well, what can we learn if we have binaries? How can we look into virus type of binaries and so on? So what I was using was like the DOS operating system because that's where the viruses were happening at the time. You have to remember the DOS operating system statically links. So all of the binaries were really big, fat binaries back then. Okay? You had 80386 computers, and we had to use the modem in order to connect to the university, right? So no phone, everyone was using the modem. No one else in the house could actually use the phone line back then. We used FTP, file transfer protocol, and in order to read all the news as to what was happening, communicate with other people, we were using the Usenet news groups. And my actual PhD work was actually done on a Unix terminal, a digital alpha machine, because that was the way that we used to do a lot of the work. You use the bigger machine to do the work, and then you generated like a target for the PC. Okay? So here you have it, like when we started the work, both my primary supervisor, Professor John Goff, and my secondary supervisor, Professor Bill Kiley, they received an Australian research grant in order to be able to look into the reversing of the C compiler to be able to convert binary programs to the equivalent C language source programs, right? And if you look at the reasoning behind it, it's because of viruses, right? That was something key that was listed here because it was like the new thing. Sorry, it's really hard to get that right. Okay, so with the techniques, like myself, I focused a lot on how to be able to lift the level of representation. If you have, if you disassemble, you have an assembly representation. Well, how can you represent like C code in a high level? So my high level intermediate representation consisted of 5 different statements. You can do assignments, you can do comparisons, you can have conditional branches or unconditional branches. You can have calls. Those calls may or may not return something, so the return was also optional. And then I had 2 other high-level transient functions for push and pop, transient instructions, because as the analysis was happening, what we're trying to do is get rid of all of the pushes and pops, right? So I applied like a lot of data flow analysis techniques, and I was just extending it and converting them, right? The Red Dragon book was one of my favorite ones. There were also like papers from Franz Allen and John Koch from IBM research labs on data flow techniques. And so the idea here was to be able to convert some of these techniques to just purely apply them to registers and also to condition codes, so that when you look at this little example, you have on the left-hand side the assembly code from the disassembly. In the middle, you have like the intermediate representation that I was using, right? And these were all simple assignments, basically. And then on the right-hand side, you have definition use change. So when you define, for example, on line 28, register AX, where is it going to be used? And it says it's being used in statement 30, right? And the idea is to be able to collapse all of these different statements to be able to create a larger statement, higher level one, that basically gets rid of all of the actual registers, and you end up with a sign to register SI, register DI, modulo 10, right? So it's getting rid of all of the intermediate registers where we're pushing things from one place to the other, right? At the same time, you also need to look into control flow techniques. And for control flow, like there were also great books available. But what's interesting is that there are all of these structures that are structured in nature, right? Like control flow structure graphs. So it all became a graph problem. And you can have like your standard composition, single branches or conditional branches, like your switch statements and conditional type of branches, pre-tested and post-tested loops. All of that is structure. We know how to represent that in a high-level language. You also ended up seeing things like endless loops, which are common in operating system code. In daemon code, you have an endless loop. So that is a valid structure. But there were others that were a little bit different, like multi-exit loops or multi-level cycle loops, multi-level exits, which are really hard to reason about, right? And you always end up needing a go-to statements. And what you're doing here is trying to collapse, right, each of the different graphs into a node. So anything that is structured can be represented into one node. Then you look at the new graph and keep on doing. However, whenever you ended up with this bottom right-hand side diagram, that's the irreducible graph. And when you have this, you need to generate a go-to. It's the only way to break it out. Or you can duplicate code in order not to have the go-to. Okay, and my colleague, Mike Van Emmerik, started working on, if Christina's doing the decompiler here in the middle, how about we don't want to be able to read all of those instructions of the 400 kilobytes, for example, of compiler initialization code. We want to be able to get to the main program that you wrote. So he started working on signature generation for both the compiler and the libraries, because all of the libraries were statically linked in. And this way, we could end up with a program that was really focusing on the code that you wrote rather than all of this other extra initialization code. And so if you think back, in the 1990s, how do you publish? Like if you're doing a PhD in one of these areas where no one is publishing because the techniques are not known, how do you publish the work? Of course, like the initial instinct is that you're going to publish at the Australian Computer Science Conference, right? Like some of the earlier work with my advisor had been published there. Every single year I submitted, and 3 years in a row it was rejected, all of those papers. So I thought maybe I'm talking to the wrong audience. So I ended up submitting to a larger type of conference, the Latin American Computer Science Conference. And to my surprise, I sent 2 papers. Both of them were actually accepted. I went to the conference, and there was interest on the papers, but I realized that I was not actually talking to the compilers community per se. So I thought I need to now go and talk to like the top compilers conference that is pragmatic, right? And that was the PLDI, Programming Languages Design and Implementation Conference. And of course, like the paper was rejected that year, and that was my last year of the PhD, right? So I was starting to think like, how does one graduate if you don't have publications, right, to really talk about your work? So I changed tactics and I started focusing on how about publishing in journals? Because in journals, there's more time for the review cycle. There's also more time for you to be able to present the work in a better way. Papers can be longer. It doesn't need to be constrained to 10 pages and so on. And so Software Practice and Experience was one of the journals where I published in 1995. And from there on was like some of the work started being published. And this is how I ended up then submitting my PhD with papers that we knew were going to be published. My PhD itself, you know, like there's some of the techniques, the decompilation architecture, control flow recovery, data flow recovery, simple type analysis. At that point in time, my advisor said, you've done enough, time to complete like your PhD, right? And my decompiler was called DCC. CC was like the standard Unix C compiler, so DCC decompiling the CC compiler, right? So there you have it. So that was the work that I actually did. But if you can think back, like the world that I was living in back then, how do you actually disseminate the work at that point in time? So I became an academic at the University of Tasmania. And back then, people used to send you postcards asking for a printed copy of your papers or printed copy of the PhD thesis. And I thought, wow, that's wild, right? So here we are shipping, like printed copies. But then email had become standard amongst universities. And so I started receiving also email from other academics or other students throughout the world, kind of like asking, oh, can you port the decompiler to Windows, or can you port it to Spark, or whichever other architecture that people were interested in? And then I was thinking, well, if I make it available, they can do the work themselves, right? So I did port it to Windows because by 1995, everyone was using Windows, no longer like the DOS operating system was the common thing to do. And what was interesting was that one day I was receiving this email message from a friend, a Colombian friend of mine, and he was doing a PhD at INRIA in France. And he said, Cristina, I was in a bus going to INRIA, overreading the paper that the person next to me was reading. And at the end, I told him, show me the front page so I can go and look up the paper to read the full paper. And it was your paper. I was like, wow, that's like completely amazing, because this was the software practice and experience paper, right? Which, amazing to think that somewhere like so far away, people were actually starting to read these papers. And I thought, oh, that's very cool. Now, because of these other emails that I was receiving about, can you port it to this architecture, or how would you do this other binary format, let's say like the COF format or whatever else, then I decided to open source DCC in 1995. And with that open sourcing, for us, like being part of the computer science department, we could have a web page. And web pages were with the gray background, as you see it, like in those photos. And at the time, you had to type all of the HTML code in order just to have like your own little page out there. And so I made available all of my publications, the PhD thesis, and the decompiler using the GPL license, because I also ended up being friends with one of the law colleagues, and we could go through what are all these computer licenses for, right? And one day, the IT guy for the computer science department comes to my office and shuts the door. And he sits and he says, Cristina, what is it that you have in that page of yours? And I'm like, well, I just have like the decompilation work, the papers, theses. Why, right? And the decompiler itself, why? Because this is the highest, largest traffic that we're receiving. And we just needed to understand, what do you have there? And why is that happening, right? And so a few years ago, I actually looked back at the archives for the University of Tasmania to try and understand how much did traffic used to cost back then. Now, this was the closest that I got to December 1998. There was a message where they actually talked about traffic. Domestic internet traffic used to be 22 Australian dollars per gigabyte, and international traffic used to be 5 times as much, 140 Australian dollars per gigabyte. And that's what I learned, like, what was the IT guy concerned about this traffic, right? You would think, lots of hits, publicity for the university, but traffic was the real issue, traffic cost. Okay, a few years later, I moved to the University of Queensland. And in the University of Queensland, I started creating this decompilation page because I realized there's a lot of information out there. There was some earlier work, that had been done on very specific targeted decompilers, going from like one particular program, how do you move it, translate it to another architecture so that the same program does the same thing, right? And I teamed up with Bill Codell. By then, the internet and email was widely available to everyone. So then doing some work with him, we kind of like had some of the earlier work. At the same time, there were other academics like Alan Mycroft focusing on type-based decompiler, which was one of those areas that I hadn't kind of like done any further work. So it was really great to be able to create like the whole page. And then at the university, Mike Van Emmerik ended up working with me, and we ended up with this consultancy where one day I received an email message from a person in New York, and he said, I have this Windows binary, and it stopped working. Can you decompile it? And us at the university were like, how does one do a consultancy at the university? Like once we figure out like how to do it, we look into this binary, and we ended up realizing that the binary had a time bomb. And so on a certain day, the binary would stop working, and we had all of the code there, and that's what we showed. And then the person that had contracted us, he says, thank you. Well, this binary, actually, the story behind it was that the lead developer had left the company and had created a competing business. And so the binary had a time bomb, a certain date, it stopped working. And so all of this work that we did actually ended up used in the litigation back in New York. Now, this one's funny. In 1997, decompilers were now being mentioned in a PC magazine in the US. And it's like we've now gone from like no one knows about these techniques to a magazine actually showing even like the web page for a University of Queensland where the decompiler is and so on. But as you can see, Cristina was able to prove that he has succeeded in creating a small decompiler. And that was one of those like, oh, wow, interesting. But nevertheless, right, like magazines were now talking about decompilers. The next year, that was my office back at the university. In 1998, I received this message from Alpha Software. And they go, Cristina, thank you for your techniques. Thanks to your techniques, we've been able to create this company that focuses on Java decompilation. I was like, oh, wow, like a commercial Java decompiler. And you should have seen like my colleague next door to me, Professor John Harrison. He was very business oriented. And when he saw that message, he's like, can I come back and reread this message? How do you mean that someone has written a decompiler, created a company, and you're not involved? And I'm like, well, that's what academic publishing is all about, right? The techniques are out there, they're available, people can use them. And then many years ago, when I was working in the US, in the Silicon Valley, I ended up getting a free lunch with the person that created this particular company. Now, towards the year 2000, everyone was worried about the year 2000 bug. And so there was this other company called the Source Recovery Company. They were focusing on very different type of machines, right? Like hardware architectures, as you can see, like COBOL assembler, MVS, and so on. And they were discussing about buying DCC. And we're like, yeah, but DCC is available, but the GPL license, of course, prevents you from using it for any commercial purposes. But at the end of the day, we never did end up working like together towards that particular issue because we were focusing on very different architectures, right? But what I did do at the University of Queensland was to put focus on what I call the cousin of decompilers, and that was binary translators. So for multiple years, the focus was how do we create a resourceable and retargetable architecture? Because retargetable compilers already existed. So everything in the right-hand side on this diagram, that already existed, right? But on the left side, no one had put focus on that. And if you really look at it, if you have a binary instruction set, you need to lift it to assembler, then you need to lift it into some intermediate representation that is high level. And then from there, you can start lowering down that representation. Well, we can try and apply all of those techniques. And so all of our focus was how to specify all of these. I teamed up with Professor Norman Ramsey at Harvard University also, because he had done some work with the SLED specification language. We also developed the SSL language, CTL, PAL, and so on, right? Like we were crazy all about this. And here's like my binary analysis group. Bulk of the work was on the binary translation work. There was some work on decompilation and some work on legal aspects of software engineering, of course, because of the decompilation work. And at the university, well, in Australia, at the time, venture capitalists started getting interested in funding computer science departments. They had heard that some new startup companies can be created out of computer science work. And so they went and they were very interested in the binary translation work. Now, at the time, you know, like trying to commercialize something at the university, in the computer science department, given that no one else had been involved in that type of way of thinking about their research, was something new, and we never ended up doing any of it because the kind of like the terms, the conditions were not very favorable to academics, but just purely because of how new it was, right? I think these days everyone has a startup, right? So the other issue was that everyone wanted us to move to another city, like Melbourne or Sydney, and my team, ourselves, were all based in Queensland, in sunny Brisbane. So none of us also wanted to move. Now, at the same time, the other side of the world, at University of Manchester, there was a group actually working on binary translation as well. And Professor Alistair Rosthorn, he used to lead this group at the University of Manchester, and they created a spin-off company, a startup company, and that company was Transitives Technology. Now, the Transitives binary translator was the one that Apple licensed to be able to have Apple Rosetta to help them migrate from the PowerPC to the x86 architecture, right? And so one of the things that I didn't know, that I only got to find out 2 years ago, was that when I did my posting on LinkedIn, Ian Rogers, who was one of the PhD students of Alistair, but also he was one of the lead developers at Transitives Technology, he responded like this, like, not just security, you know, like your work was also inspiration for the binary translation work that they were doing at the time, right? And so it's just truly amazing to hear some of these stories. Now, because no one had ever, you know, a workshop on decompilation, I decided to have one. And anyone that uses IDA Pro, you know that Ilfa Gulfanov is the lead developer for like the IDA disassemblers and now the IDA Pro decompilers, right? So at this workshop in 2001, I ended up meeting Ilfak. And so Ilfak is the third one here, Mike on the left-hand side, myself, Ilfak, and Trent Warrington, who was one of our students at the time. And with Ilfak, it was like super interesting because we got to actually talk about how to create a decompiler. I mean, he was working with commercial disassemblers, right, like the IDA Pro. And he had ideas of creating a commercial decompiler. And so we did like a lot of exchanges of information and so on. Now, meantime, a little bit later, I had a consultancy in the US. By then, I was living in the Silicon Valley, and I did this 2 days training. One company approached me with, we want to learn how to do a decompiler, how you write it, can you train us? I wrote like all the training materials for them, but I said like, you need to give me access to your hardware, like all the specifications for the assembler for that machine, as well as any other information, right? And with that, they send me a full kit. I go and work on that, and I use the IDA disassembler actually to be able to see how well this would work, to then be able to explain what are the next steps to write your decompiler. And here's a slide like that I had from this training in January 2003. There were no commercial decompilers at the time. If you needed one, you either go to a company that offers a service, a decompilation service for you, or you needed to write your own. And that's basically what they were trying to do, how to write their own decompiler. Now, same year, I ended up meeting Chris Weissapol. Chris used to work at the time at Symantec, and he was one of the directors of development. Chris is well known for his ethical hacking techniques. He was part of Loft, and he's giving testimonials at Congress and so on. Now, when I met him, he told me, like, we've been using like your decompilation techniques to be able to find vulnerabilities in binaries. So they wanted to be able to create this and make it like a new type of service available. And so they were trying to spin off from Symantec. So I talked to their venture capitalist, and the venture capitalist said, like, thanks to like the information that I provided, they decided to be able to fund Veracode, and that's what led to this company, Veracode, to be available. Veracode, up to today, still alive. Like, of course, they have diversified like their products, but they have provided decompilation and vulnerability finding services on binaries for many, many years on end. And now they also look into like the bigger, like ecosystem, not just only binaries. Now, Ilfak, he started working on his decompiler. In 2003, he has, like significant results through like a real-life Trojan that could be decompiled. Then he created a new company called Hexrace. And in September 2007, he made available version 1.0 of the first decompiler. Right? And so this was like the first original decompiler for binaries that became available in the marketplace. And then other years later, 2016, there's another company called Vector 35. They made available Binary Ninja, but they also went through several steps. Initially, they were creating a proof of concept using Python and so on. But in 2016, they ended up releasing like their version 1.0 of Binary Ninja. Binary Ninja these days, also a commercial decompiler. Various different people use it. One of the key things that they did in their intermediate representation was to use static single assignment form, or SSA. And SSA was actually one of the techniques that was pioneered by my colleague, Mike Van Emmerik, in his PhD thesis, right, in 2007. So it's kind of interesting, like, to see, like, the weaving of all of these techniques and knowing, like, who's a player in this particular space. And now, a few years ago, in the US, the National Security Agency, NSA, made available their Ghidra decompiler. And they open sourced it in April of 2019. Now, their focus when they open source the decompiler was on looking into malicious code, being able to generate indicators of compromise and things like that, right? When Ghidra became available, of course, there was a lot of talk about like where did these techniques come from, and is there a parallel to what Cristina was doing, and so on. But there were no acknowledgments at the time anywhere in the documentation. However, like in 2 years ago, the documentation was updated, and Ghidra actually has this acknowledgement about their decompiler. It was based on the design, right, that I had created in my thesis, the disassembly, the translation, the data flow, the control flow, and then backend code generation, right? And also having an intermediate representation that is resourceable and retargetable, that had also kicked in into their work. Their intermediate representation is called a slate. And then they had like further information as to how they picked up some of this information also coming from the binary translation work to feed into their decompiler, right? So it was really, really cool to see all of this come to life now. So since then, my teams have started using the compilation techniques. And here's where things start becoming like meta-circular, right? Techniques that I developed like 32 years ago started being used by my own teams because commercial decompilers and open source decompilers were not available. And so ColdPress was one such example. This work with my colleague Mahin Chandramohan and one of the interns that we had at the time, Haokshi. All of this work is actually open source at the University of Queensland. And the idea here is to be able to extract indicators of compromise from Windows binaries, just purely focusing on static malware detection. And so we created the architecture on the left-hand side where now you're orchestrating multiple different tools. You're getting information from various different compilers. We had Ghidra, Radar, and other decompilers, including academic decompilers, right? And then you have like threat intelligence coming from various different places to be able to determine what are the indicators of compromise, start summarizing all of this information, and then doing it all automatically, right? So this work, like I say, is open source. Later on, we use this infrastructure to convert it into like a native cloud service to be able to scale up better. And now, more recently, of course, AI, everyone is leveraging AI, right? And at Oracle, we changed the style of the slides because this is Oracle work from this year. Also, my colleague Mahin Chandramohan and Rodrigo Branco, there have been like various different works focusing on how to augment decompilation with AI. And I'm going to talk about like two of these cases very briefly. The first one is how to do binary diffing. So you have two different binaries. You're interested in being able to know if a particular CVE that exists in the wild that is already known exists in the binary that you're interested in looking at. Now, it may be that that CVE exists in exactly the same form, or it could be a slight variation of it, right? And so for this purpose, like what we're doing here is taking like a lot of the data like from open source CVEs. There's CVE patches that are made available. We also look into purely focus on Linux, right? And so for Linux, there's strip binaries, there's debug binaries. We can take like and generate all of the signatures for more than 20,000 different open source libraries and focus on Linux kernel vulnerabilities to then be able to put all of that into a knowledge base. And our knowledge base is actually using the BSIM extension of Gitra to be able to do like the binary similarity. You have like your binaries, like debug and strip. You have the CVE patch and so on to be able to generate like this large knowledge base here, vulnerability knowledge base, right? This is all an offline process. You do it once, you have this knowledge base, right? And of course, you can be augmenting your knowledge base as time goes by. So then when you want to use it, what we're doing is we're taking like target binaries that we're interested in looking into. We're taking like the binary BSIM, like binary diffing, and then rather than passing to the LLM, here's all of the information. Here's the binaries and here's like the CVE that we're interested in. We're actually doing an optimization to be able to reduce the number of tokens that need to be used. So if we were going to do this type of analysis raw, like the LLM would use 1 to 2 million tokens, whereas if you do the optimization, finding the top K candidates for the vulnerable functions, you actually reduce it to 100,000 tokens. So significant optimization that helps you get like quicker results at less cost as well. And another example of work that we're doing with agentic AI workflows now is to be able to take like rule-based vulnerabilities to be able to detect those vulnerabilities purely based on rules. And in this particular case, we're leveraging some work that has been open sourced recently in the past 6 months by Binary, which is called the Vol Hunt rule generator, right? And so here, again, you're going to take information, lots of data, right? You're going to take like debug vulnerable binary, the strip vulnerable binary, Gitra, you're going to be able to do the decompilation, CVE patches, you're going to take the documentation on Volhunt documents, right? And you're going to send through patched binaries as well, both in stripped and non-stripped debug versions, right? And so the idea is to be able to use a fully automated agentic AI workflow to be able to generate rule validations. So with the rules, generate a rule validation, and you're testing it with unseen stripped binaries, right? So if we know, for example, that here there's a particular type of CVE, but this binary has not been seen anywhere else in the process, it gets used here for validation, and the rule validation engine keeps on being iterated on until it can get this information correct. And then this way, it ends up sending new rules that can be used, okay? You can end up with like various different rules that are well-formed, but you can also end up sometimes with rules that are brittle if you don't have enough context information. So context, super, super important in order to be able to do this type of leveraging of information. Also, optimizing your LLM token usage, super, super important. And of course, the data quality is going to be like key for any of this security type of work because, you need to know where the vulnerabilities are when you're sending training data, all right? So to conclude, what have been some of the coolest moments over the past, 32 years now? Initially being able to receive like a Sun Microsystem hardware grant to be able to do the binary translation work, that was super awesome. Being able to receive like a free lifetime complimentary license to IDA Pro, that was like truly amazing. Joining the Veracode Board of Advisors at a time when I didn't even know what a Board of Advisor was. That was also like interesting. By 2020, my team's actually using decompilers. That was like so meta-circular. It was like super awesome just to see. But then later on, seeing the acknowledgement by the NSA, by GitRA. That was like fantastic, receiving free license to Binary Ninja. And then 2 years ago, receiving the Lifetime Achievement Award on Decompilation. That was like amazing. But most of all, right, there's all of the thank yous that I receive at various different conferences, all of the hallway discussions. People come and tell me what they're doing with Decompilation and so on. It's just amazing. So with that, I want to thank you for listening to my talk.